Hello folks, welcome to our continuation of conversations about integrals. In this video we are going to talk about one of the things we do when we can't integrate. So we have been talking about slope fields and how you can use a slope field to approximate a y value. In other words, you can solve an initial I'm going to put that in quotes, an initial value problem by kind of cheating it with the slope field, right? So in this case, I could say, okay, it wants me, I've got the slope field for this differential equation. It's saying, I'm telling you that it contains the point -3, -4, so I can come down here and put a point around -3, -4. Okay, and then it says they want us to find y of 2. So in other words, what I'm going to do is follow this slope field, right? I'm going to see. I'm going to do the best I can here, right? And again, we're all going to sketch this path a little differently, and then we're going to say, all right, y of 2. All right, I'm calling it right around 3, a little bit bigger than 3. Obviously, this is not the greatest method anybody ever had. Okay? As you saw when we did our approximations, depending on how you sketch the curve, depending on how you read those tangent lines, everyone's going to have a little bit of a different answer. The chances of two people getting the same answer doing this, pretty low. And we really don't have any way of knowing how accurate we are either. So this is kind of not the greatest plan anybody ever had, but it is helpful, right? What we want to look at is a way to do what we just did, but be able to tell at least minimally how accurate we are and be able to all land on the same number. In other words, we want a process that we can go through for approximating where we have some control over it, right? Where we say, you know what, now I want to be more accurate, or I don't need to be that accurate, right? I'm launching a rocket, I need to be really, really accurate, or, you know, I'm building a garden. I don't need that many significant figures. I don't know why you would need a slope field to do either of those things. I'm just spitballing here. All right, so what we want to do is have a foolproof, these are the rules. If you want to move your way through a slope field, this is how you do it. Because in math, you got to have a right answer or we get uncomfortable, right? We're not, even when we approximate, we want there to be a correct approximation, dang it. All right, so that method, that rule, that process is what we call Euler's method. Okay, Euler's method is a process that we use to navigate through a slope field to get from the point I know to the point I want to know. Okay? It's literally just mathematically following a slope field instead of visually following a slope field. Okay? So the idea behind Euler's method is that what we're looking at when we look at a slope field is a bunch of pieces, itty-bitty lines, right? Tangent lines specifically. And we know, thanks to local linearity, that those tangent lines very closely approximate the actual function we're looking at as long as you don't move very far, right? So what Euler's method does is it says, okay, look, you're in a field of tangent lines, right? We're going to take steps through that field, and we're going to follow the tangent lines. And Euler's method says, look, we're just going to take tiny steps. As long as you take tiny steps through a field, you'll never be too far off your curve. So if I'm on the tangent line at the point -3, 4, and I take a big step, I'm probably nowhere near that curve anymore because I followed the tangent line and not the curve. But if I only take an itty-bitty step, right? If I'm here and I only take an itty-bitty step, I'm going to be pretty darn close to the curve, right? And so the lines in a slope field are pretty little, right? So I'm just going to follow it a little bit. And then I'm going to say, okay, well, where am I now? Let me reevaluate. What tangent line am I at now? And change direction, right? So we're going to take a step, change direction, take a step, change direction, take a step, change direction. And we're going to create these little tiny steps through the field, but we're going to do it numerically. We're going to actually use the equations for the tangent lines so that we all get the same answer. We're not just going to eyeball it. Okay, so here's the process. First thing we're going to do is we're going to write an equation for the tangent line at the point that we know. Okay? So for example, in this problem, the point that they know is this point right here, 2, 0. So they wrote the equation for the tangent line at 2, 0. And here's what I know. At that moment, I am on the curve. I am on the curve at that moment. Okay. As soon as I take a step, I'm not going to be on the curve anymore. But at that moment, in the very beginning, when you write the equation for that first tangent line, we are on the curve. That's the definition of a tangent line, right? It matches that point. And so what we're going to do is we're going to take a step along that tangent line. Notice the distance, the width of the step they took was 0.2. Right? So they didn't go very far. Right? But they followed the tangent line, not the curve. Because remember, I don't know the curve. I don't know the equation for the curve. I do, however, have an equation for a tangent line. So I'm going to say, okay, well, what if x was 2.2? What would my y value be? And what I get from my tangent line is a y value that's darn close to the real one. Right? And now I have a new point, right? I have the point 2.2 with a new y value. Now, is that point on the curve? No. But is it close to on the curve? Yes. So from my new point, I draw another tangent line. Or I write the equation for another tangent line. It's going to take me to x is 2.4. And I say, okay, tangent line, if I moved 0.2 along this line, where would I be? And it gives me this new y value, right? And you can see here, this, I'm kind of getting away from the curve, right? And when I take my next step, I'm starting to move away from the curve. The further you go, probably the further you're going to move away from the curve. Okay, want to stick closer to the curve? Take smaller steps. So we can kind of control how accurate we are, either by not moving very far away from the point of tangency, or if we need to move far from the point of tangency, take tinier steps. Okay? So again, this process here, if you're taking notes, so we're going to write the equation for a tangent line at the point that we know. Use that equation to approximate the next point, where I am. I'm going to take a step mathematically on that tangent line, find a new point and a new slope, because after all, I do have a differential equation. Once I have a new point and a slope, I do it again. I write another equation for a tangent line. I take a step on that one. I get a new y value. I get a new slope. I do it again. This isn't a difficult process. We're writing equations for tangent lines over and over and over. It is a tedious process. It's going to remind you very much of Newton's method. If you remember when we did Newton's method, we drew a tangent line, we found it's 0. Then we drew another tangent line, found that 0. Drew another tangent line, found that 0. And we figured out that the more times we do that, the closer we get to the actual 0. Euler's method is similar. It's just that doing it more doesn't make you more accurate. Right? Doing it more moves you further from your point of tangency. So now we want to make tiny steps. That's what's going to make us more accurate. The smaller the step, the more accurate we will be. All right, so again, we're going to go through the mechanics of this and actually do the calculations when we're together, because I can't even imagine how boring it would be if I actually went through that in this video. Okay. What we're going to do is we're going to write an equation for a tangent line right here. Okay. So I'm going to say, let's say that the slope right here is 1, just for fun, right? So I'm at the point 2, 0, and I have a slope of 1. I can write the equation for this tangent line right here. Be y minus 0 equals 1, x minus 2. So y is equal to x minus 2. Right. And I say, okay, hey, tangent line, if I follow you instead of my curve, if I follow you to 2.2, what would my new y value be? And tangent line says, your new y value would be 0.2. So we say, oh, okay. So now where am I? Now I'm at the point 2.2, comma 0.2. That's where I am now. I use a differential equation. I find the new slope. I do it all again. Right? I get the equation for a new tangent line. I follow that tangent line over to 2.4, and so on and so on and so on. So what we're doing is the same thing we were doing here. We're just taking very measured, specific steps. Instead of just eyeballing it and going, I think it goes this way, we're actually going to write the equation for a tangent line, follow it a step. Write the equation for a new tangent line, follow it a step. Write the equation for a new tangent line, and create a little string of tangent lines. And again, here comes local linearity, right? We're going to have a string of teeny tiny lines. The tinier your lines are, the tinier your steps are, the more closely it will mimic a smooth curve. You take big steps, you're going to get a, right? You take little steps, you're going to get a nice smooth curve. Okay. More steps will be more better. Now, obviously, they're going to have to tell us how many steps to take, right? Give us a way to know how many steps to take so we know when to quit, right? With Newton's method, they would say either be this accurate or do this many iterations. And they've got to do that with Euler's method too, because otherwise we would not know how big a steps to take. The problem is never knowing when to quit. Because we have a final destination with Euler's method. I know, for example, in this problem, I need to start at this point, and when I get to 2, I need to quit. Right? So I know from the giddy up how many steps I need to take. The question is, how big do those steps need to be? And they're going to have to give us enough information to tell. All right, so let me know if you have any questions on this, and tomorrow we will do an actual numerical iteration of this. You're going to love it.